Okay, so now let us look at these propagations of action potential. Okay, now what is mean propagation of action potential? We have to know that action potential is not like an electrons that can move along. Okay, action potential, they don't move along the axon or any neurons. The reason is because action potential is localized. It's a localized event. Are you clear? It's a localized event. But this localized event set up a local circuit so that it can induce the next regions to have action potential. Okay, so basically we have to know the action potential, they do not travel along an axons, but what they do, action potential, okay, any action potential at any point of the axon can trigger the productions of an action potential in the membrane of the either side of it. I call it as a neighboring site. Okay, so let me show you guys how this action potential can take place. Okay, so look at this diagram. So let's say this is a first region, this is a second region, third region. It's the what we call this something like animations. This is t equal to 0, t equal to 1, t equal to 2. So action potential is characterized. Action potential is characterized by what? Massive, rapid influx of the sodium ion. Can you see that? So it means that if I have the massive influx of sodium ions, so action potential is generated, correct or not? Because if you want to generate action potential, it's characterized by rapid depolarization followed by the repolarization. So it means that when a sodium ion enter into this region, there is a rapid influx, a lot of sodium ion enter. So what will happen here is sodium ion repel each other, right? Positive, positive, so they repel each other. So when they repel each other, some of the sodium ion enter to the second region of the neuron. When it enter the second regions, it stimulates the regions, kind of, it becomes depolarized this region. When depolarized the region reach the threshold value already, then you can see that now all voltage gated sodium ion channel open, so allows the sodium ion to enter. So when the sodium ion enter here, now see, when the sodium ion enter into this region, what will happen? So it will trigger the action potential. So can you see action potential now move from region number 1 to region number 2? Okay, so when the sodium ion enter into the region number 2, what will happen? They repel each other. So some of the sodium ion move backwards, some of the sodium ion move forward. Those that move forward, no problem. Move forward, what happened? When they move forward, then it's going to cause the depolarization and followed by the rapid depolarization. Correct or not? Okay, so action potential now, can you see that? Transmitted now to the third region, from the first region to second region, now to the third region. But how about the previous region? The previous regions now right now, they undergo absolute refractory period. At this moment, because this part at t equal to 0, okay, the first part of the neuron here, okay, experience the massive influx. So means that now they are in slight rapid depolarization. So followed by what? Followed by the repolarization. So repolarization here basically means that all voltage gated sodium ion channel close. So it means that if all voltage gated sodium ion channel close, is similar to, I say that time's up, you cannot submit your assignment anymore. So therefore, even though you have stimulus, you won't be able to generate action potential at this the backward region. But forward region, yes, forward region still possible. So that's meant by the action potential now transmit. Can you see that? Action potential now transmit. Okay, so I draw diagrams, then you can see. Okay. So later I'm going to use again one. Phase 1 is the resting potential, resting stage or resting potential. Okay, stage 2, we know that it's a slight. Okay, depolarization. Stage number 3, rapid depolarization. So my focus will be here. And number 4, repolarization. And number 5, okay, will be hyperpolarization. But as I say, that's my focus will be these two, 3 and 4. Okay, 1, 3, and 4. Sorry. Okay, so let us look at this, the neurons. Oh, sorry. Yeah, so this is a terminal receptor there. So this is T equal to 0. T equal to 1. Same neurons, it's just a different timing. T equal to 2. So at T equal to 0, okay, so I divide them into 3 regions. Okay, so 3 regions. So this is region 1, region 2, second regions, and the third region. Okay, now what should happen here is the first regions, okay, before T equal to 0, they are at the resting potential. Okay, resting potential. Number 2 also at the resting potential. Number 3 also at resting potential. What will happen here if at T equal to 0, we give them the stimulus? So stimulus actually cause the slight depolarization, slight depolarization. And if reach the threshold value, then you can see that at region number 1, action potential is generated. So now we enter into the phase 3. But how about number 2 and number 3? Number 2 and number 3, region number 2 and number 3 is still resting potential. Continue, nothing, right? Continue resting potential. So all at stage 1, resting potential, all resting potential. Okay. Now, what is the main events that happens at phase number 3? Rapid depolarization. So basically, they have the entry of the sodium ion. So a lot of sodium ion. So some of the sodium ion now repel each other, enter to the region number 2. So this one is T equal to 1 millisecond now. Okay. So what will happen here is, because the entry of the sodium ion into the region number 2, now you can see that initially in the resting potential, now you can see that they start to depolarize, okay, slight depolarization, and then rapid depolarization. So region number 2 now is triggered, kind of stimulated. So it means that now at stage number 3. Can I see that? But how about the first region? First regions now, they already done the stage number 3, the rapid depolarization. Okay, red color is current, okay, so green color is means previous ones. Okay, previous one done already. So now they are in stage number 4. So what is the characteristic of stage number 4? Repolarization. So repolarization characterized by what? All voltage gated sodium ion channel closed. So impossible to generate any action potential now. No, impossible, because all voltage gated. Okay, all voltage gated sodium ion channel closed. Are you clear? Okay, region number 2. Region number 2, you can see that sodium ions enter, right? Sodium ion enter. So sodium ion can go to both direction. So it go to the backward, no problem, because all voltage gated sodium ion channel closed, you cannot generate any action potential. But when it go to the region number 3 at resting, then you can see that in times T equal to 2, what will happen here is, because of the sodium ion enter, right? Sodium ion enter. So what happened? You can see that now they experience slight depolarizations, continue with the rapid depolarization. So action potential is generated. Can I see that? Action potential is generated at the third region. But how about the second region? So action potential is generated basically means that sodium ion enter, right? A lot of sodium ion. So sodium ion can repel each other, can move to backward region. But at this region now, you can see that the membrane is undergoing repolarization. So again, no action potential can be generated. But at the third region, yes, we have the action potential. So if I minimize the diagrams here, you can see that, Okay, so first at the first regions, we have action potential, trigger the second regions to have the action potential, and then continue. But backward movement is impossible because of the absolute refractory period characterized by what? All voltage gated sodium ion channel closed. Therefore, no action potential can be generated. Are you clear? Okay, any questions so far? So what is the function? Now you have to know what is the function of, what is the characteristic of the absolute refractory period? Absolute refractory period means that no action potential can be generated, characterized by all voltage gated sodium ion channel closed. Are you clear? All voltage gated sodium ion channel, they are closed. Okay, so what is the function? To prevent the backwards transmissions of an action potential. Okay, that is the role of the absolute refractory period. Okay. So you can answer the questions here. Okay, you can answer the question. Simple ones. Okay. So how about the speed of the propagation of action potential? So the speed of propagation of action potential depends on two factors. Okay, first factor is the diameter of the neurons. Second is the presence of the myelin sheath. So as we know that the larger the diameter, the higher the speed of transmissions. Okay, always remember it's something like a highway compared to a small road. Highway you can speed, small road you can't speed. So the larger the diameter, definitely the transmissions of the action potential will be low. As I said, the larger diameter, the higher the speed of the transmissions. So because resistance is low, okay, low resisted. So therefore, those animals with the giant axon will speed up the transmission, result in the very rapid responses to escape from the danger. Okay, but sometimes, we want to, we cannot accommodate. Let's say, for example, small organism, how they accommodate the giant axon is impossible. Are you clear? So it's very impossible for them to have the giant axon. Okay, so in order to improve, or evolution to take place, then you can see that the neurons is myelinated neurons. Okay, myelinated neurons. So what's mean myelinated neurons? Myelinated neuron basically means that they had the stem cells wrapped around at the regular interval. Now, what happened here is if you wrap around at the regular interval means that action potential cannot be generated at this interval. Are you clear? So means that the action potential only can take place at the node of Ranvier. Now, how it become faster? Now, look at this. If let's say without, I draw it out. Okay, follow. Now, if without myelin sheath, okay, T equal to 1, T equal to 2, T equal to 3, action potential ungenerated, T equal to 1, T equal to 2, T equal to 3, T equal to 4, T equal to 5, 6, 7. So they need 7 milliseconds, let's say, for example. Can you see that? Without myelin. Okay, so okay, now 1, 2, T equal to 3, T equal to 4, T equal to 5, T equal to 6, T equal to 7. But if let's say I have the myelin sheath to cover at the regular interval like this, so means the action potential only can be generated at the node of Ranvier. So look at this, T equal to 1, T equal to 2, T equal to 3, T equal to 4. Can you see that? So time taken now will be shorter. Because why? At the myelin sheath here, no action potential can be generated. Why? Because the myelin sheath cover the neuron. So it means something like insulate the neuron. Basically, sodium ion cannot enter, potassium ion cannot go out. So only at the node of Ranvier, the action potential can be generated. So it means that the first regions here will induce the second region induce. The concept's still the same. It's just that at the site where you have this myelin sheath to form this formed by the stem cells, those parts, no action potential can be generated. Are you clear? Now, you may say that, oh, so long distance, then can the sodium ion move? The answer is yes. Okay, why? Because even though we draw it large, there's our cells, so very, very tiny. The distance few, you can see that about few micrometer only. You have to imagine it's a cells. Okay, so drawing part, you can see, very long, but no problem, because in actual case, in the cells, they are very, very tiny only. So this tiny gap allows the speed of transmission, and this kind of transmission, it seems like the action potential jump away from one node to another node, right? Jump. It's not continuous. It's not like but now you see that it's something like jumping. But again, I wouldn't say jumping, because this mode of transmission, we have a correct term to describe. It's called saltatory conduction, right? Saltatory conduction. Highlight the word. When answer the question, this one you have to put in. So this mode of transmission is known as saltatory conduction. Okay, so increase the speed. So you can look at this diagram now. You can look at this diagram to show the difference. Now, let's say I take this. Okay, let's say I take this. If I want to achieve 20 meter per second, the speed. Okay, if I want to achieve 20 meter per second, then you can see that for unmyelinated neuron, it's roughly about 200 micrometer. Can you see that? It's roughly about 200 micrometer. But for myelinated neurons, you just need about like 7.5 micrometer. Okay, so means that if you look at, we need to have 200 micrometer compared to the neurons with 7.5 micrometer. So means that the space that we use to accommodate one neuron, now I can accommodate many neurons. So that's why in some mammal, or most of the mammal, our neurons actually, they are myelinated neurons, smaller diameter, but we can pack them more, so increase the sensitivity. So that's why, a lot of mammal actually, we can actually sense danger faster. Why? Because our neurons, we have more neurons. It's more accurate in this case compared to some of the primitive animals that they only have the unmyelinated neurons. Okay, so we have one disease called multiple sclerosis. So multiple sclerosis is the autoimmune disorder result from the gradual deterioration of the myelin sheath. So means that degraded. So means that the speed of transmissions will be very, very slow. Okay, progressively the muscular weakness and dysfunction. Because why? They can't receive any action potential already, and slowly it will cause the death. Because why? Multiple sclerosis, at the end, you can see that your central nervous system cannot function, your smooth muscle cannot function. So at the end, you won't be able to survive. A person with multiple sclerosis, and there is no cure. Okay, because if you look at this, okay, if the neuron with 5, okay, you can see that if a neuron is 5 but unmyelinated, so unmyelinated 5, basically the conduction is near here. Can you see that it become unmyelinated? So means that the process of the transmissions, or the speed of transmission, will be very, very slow. Okay. So how the action potential carry the informations? Okay, how the action potential carry informations? Basically, we do know that all non-principal, the intensity of stimulus have no effect on the amplitude or magnitude of the action potential. They're always the same. Can you see that? Always the same. Okay, but the strong stimulus can be differentiated from the weak stimulus by their frequency. Always remember, this one determines by what? Determines by the relative refractory periods. Okay, relative refractory period. Okay, a strong stimulus produce higher frequency, and also the strong stimulus likely to stimulate more than one neurons than the weak stimulus. Are you clear? So how? Now let us look at how we can generate greater frequency. Okay, let us look at this. Yes, strong stimulus. Now let me draw this again. So this is a resting potential, -65. Then we have the threshold potential -50. Okay. And then you have the maximum +40 for the membrane potential. Now look at the first stimulus. Okay, we generate first stimulus. So basically we can reach the threshold potential and then we get, okay, and then come down. Now, hyperpolarization. Okay, so now I want you guys to look at this. From -65 to -50, this is, okay, the gap we need to fill up. Correct? Okay, we need to fill up. But now, if the cells already undergo what we call the relative refractory period, can I generate new action potential? The answer is yes, but cannot be the same strength. Why? If the same strength, let me complete here. Okay, where is my, okay. If I copy down this part, so can you see that with the same strength, can I reach from here? Now I cannot start from that. Can you see that? I cannot start it from the, let's say here, -70. If I start it with -70, with the same, okay, with the same amount or same intensity, I can't reach the threshold value. But if I can increase the strength, then the answer is yes. So within a short period of times, I can reach the resting potential, reach the threshold, and I can get the action potential. So duration from one action potential to another action potential is shorter. Can you see that? If the higher strength. But if my strength is remain the same, the strength didn't change, what will happen? If the strength remain the same, what happened here is I have to wait, slowly wait for my resting potential to be maintained first. Then with the same strength, I can achieve the threshold. And again, so means I can see that I need to take longer period of time to achieve or to make the second action potential. So the brain will interpret this action potential based on the frequency. Are you clear? Based on the frequency. So means that you can see that A will be a strong stimulus. Okay, why strong stimulus? Because more. B, can I see that? Less action potential, your brain actually interpret it. Are you clear? So to get the information about the strength, the stimulus being detected, the brain can therefore interpret the frequency and the number of neurons that carry the action potential. So it means that if, let's say, the frequency is very low, only 1 or 2 neurons, so it means that the signal is very, weak signal. But if, let's say, it's very strong signal or stimulus, oh, many. And then the number also higher, okay, the neurons. Okay, but in terms of this type of the action potential, receive 1, receive 2, receive 3. So how our brain actually interpret? How our brain interpret, oh, this is a pain, or this is the light, or this is a hearing, this is the taste. How? Basically, okay, the nature of the stimulus, where is the light, heat, touch, or so on, is deduced by the positions of the sensory neuron bringing in the information. So it depends on where the sensory neurons coming from. If the sensory neuron coming from the eye, so those stimulus, automatically our brain will interpret it as the light. Okay, so now I want you guys to try this. Okay, now I go through this one first, then I'll tell you more about this. Okay, now, so for frontal lobe, so detect what? The movement of the body, the speech, the smell from the frontal lobe. Okay, for example, for hearing will be temporal. Okay, occipital lobe is the one that you have the brain regions that detect what? Detect the light. Can you see that? Okay, so we have the cerebrum and limbic lobe. So we have those parts of the brain where our neuron will be connected to, and then from there we will be able to know whether which kind of the stimulus. Okay, so do not need to remember these extra informations for you guys. I forgot to it, so it is for your informations only. Okay, so that's how our body deduce. Okay, so with this, I have done for today's lesson.